Hi, today we're adding one more layer on top of everything, but this is probably the last big layer we're going to be adding. When in class, I usually present the following scenario. You are a crime scene investigator, and typically this is the largest application of chemical quantities. This whole field of chemistry known as quantitative analysis, quantitative chemistry, analytical chemistry. The idea that you want to figure out something about your chemical that you don't already know because you don't have information. If you were working at a crime scene and you found a chemical on what you might believe to be a murder weapon, you would need to analyze it to figure out what that substance is and if that could somehow be helpful. And sometimes the answer is no, but you still have to go through the process. And so one of the things you can get is an elemental breakdown of what your substance is composed of, as you see here. And so going through the journey to figure out what chemical it is might be pretty beneficial, and we're going to do that. Before we get too far into that specific example, though, one of the things we talked about before, this was one of the problems we saw in class where we had 80% carbon by mass, 20% hydrogen. If you need to see me go through the work of how to get to this empirical formula of CH3, I'll do it now. And here it is. Percent to mass, mass to moles, divide by the smallest. We're in a 1:3 ratio. That said, this is not what we would call a molecular formula, which is the actual numbers of each element found in your compound. If we tried to draw a Lewis structure for CH3, you get this, which is not stable, octet invalid, for lack of a better term. So in the case that you get this impossible chemical compound, the actual chemical compound could be some multiple of that empirical formula. Each of these is a multiple of that 1:3 ratio. This would be times 2, times 3, and so on. And the idea being all 5 of these chemicals have the same empirical formula of CH3, but different molecular formulas. Now, in this case, it might not even be that big of an issue. I'm not going to take the time to do this, but if you tried to draw all of these chemical compounds, 4 out of the 5 of these are invalid by that whole octet stability design. And so the only chemical compound of this list that has the empirical formula of CH3 and is a valid chemical compound, is actually possible to exist, is C2H6, otherwise known as ethane. But this is a bit of a problem. I believe this is either inductive or deductive reasoning, and it's not what we want to be doing. We don't want to consider all options and narrow it down to one. We want to use the information we have to guide ourselves to an answer, because I don't want to take the time to figure out all of this, what is possible and what isn't possible. I don't know. If we kept going 6, 7, 8, 9, 10 carbons, would another one be, would that potentially exist? And so instead, we need to gather a little bit more information. Now, going through the information from the previous slide about the mystery, we've got our percentages here. Let's quickly figure out an empirical formula. Time sign line, 1 mole, 12 grams of carbon, right? That's from our periodic table. 1 mole is 1 gram of hydrogen, and 1 mole of oxygen is 16 grams of oxygen. I'm rounding to the whole number just to make everyone's lives a little bit easier. Of course, you're welcome to take more decimal places. 3.333 divided by itself is 1. This gives us an empirical formula of CH2O. Great. Except, unlike the previous example, all 3 of these chemicals here have the empirical formula of CH2O. And all 3 are actual valid chemical compounds. This one is formaldehyde, this one is acetic acid, the active component of vinegar, and this one is glucose. And if you add it up, you would get a 1:2:1 ratio of carbon to hydrogen to oxygen. So again, we need more information because all 3 of these compounds are 40% carbon. All 3 are 6.67% hydrogen. All 3 are 53% oxygen. So one of the easiest ways to get from that step of the empirical formula to a molecular formula would be if you were provided a molar mass or a molecular mass. This is the actual thing that's there. The idea being you can do a lot of this math to get from your percent composition several steps to empirical. You're then adding one more step to molecular. This is the step we're focusing on here. So it does rely on you having all of this other stuff figured out already. So if we have the molar mass And we know that the empirical mass and the empirical formula are related by some sort of whole number. Well, what if we had this empirical mass? 2 carbons, 4 hydrogens, and 1 oxygen. That would be 44, give or take, grams per mole. Well, so molecular mass. The idea is that the math that the masses undergo is also the math that the formulas undergo, because the mass is, of course, dependent on the formula. If we can figure out what math it takes to get from empirical to molecular here, which would be times 2, right? 88 over 44 is 2. Then the same thing must be true here times 2. And so we multiply all of the numbers here by 2, we get C4H8O2, and this would be our molecular formula. So in general, as long as we can get this molar mass here, if we can calculate or are given the molar mass, we can then translate the empirical formula to a molecular formula. So here's another situation. If you want to do some of the first bits of the calculation yourself, you can. I'm going to start now. So we assume, of course, a 100-gram sample. You're welcome to assume any mass you want. It will end up working out the same way. We're going to divide all 3 of these by the smallest. We get C2.5H5O1, which that doesn't work. We're going to have to multiply back. And this is not the multiplying back we just did previously. This is the multiplying back because we're not at our empirical formula yet. C5H10O2. You can't reduce that down anymore. That is the simplest ratio. So that's our empirical. We need our empirical mass, which is 102. Now, in this case, we were not given an exact gram formula mass or molar mass or molecular mass. Actually, this should be a gram molecular mass. Let me finish that because this is a covalent compound. But we could employ a little bit of reasoning and logic here. If we're looking for something between 202.6 and 207.26, and our empirical mass is about 102, well, the only number that's a multiple of 102 and in between these two numbers is 204, and 204 divided by 102 is 2, which means that our molecular formula would be C10H20O4. I don't really know what that chemical is. I'm going to assume it's possible, but this would be a good point to take this and then go do some further research. Does this chemical exist? What does it look like? What are its properties? Does this match any of the other information you have if you are this hypothetical crime scene investigator? I don't know if it's super obvious that I've been slowly working my way through Bones, the series, while teaching this year. Finally, here's one other way that you could possibly see the information presented. Not that this is the last way, but this is the last way I'm going to show you. Again, we're going to use the information from our first slide here. We know from this information our empirical formula is CH2O, right? So if you need to go see that again, you can rewind and go check that out. We know this mass to be 30 grams per mole for the empirical. So here's what else we know. If you had a 0.4 gram sample, we were able to figure out, someone somewhere was able to figure out how many moles that represent. So to get from our empirical to our molecular, we need to know what the molar mass is. Remember that that's the mass of 1 mole. So what we have here is the mass of a smaller number of moles. I think it would be helpful to set up a proportion with our given values on the left, and we're trying to figure out what the mass of 1 mole is, right? That's our molar mass, our gram formula mass, our gram molecular mass. And so we're targeting this unknown on the top. Let's call it x because that's a good number. We could cross multiply, solve, right? The moles here are going to cancel when we cross multiply and actually do our division. And then we will get, oh, look at that. So in this case, x is going to be 179.8 grams per mole. Or grams, because we're talking about 1 mole here. So again, we're going to use this empirical mass. This is our molecular mass, so let's set up our proportion. In this case, we're going to have to do a little bit of rounding because we didn't use exact masses initially. We don't know if there's maybe some slight error, but obviously it's very, very close to 6. So in this case, our molecular formula would be 6 times larger to give us C6H12O6. So of the 3 examples we saw before, glucose was the most likely actual chemical based on this second bullet of information. That's how you use this added piece of information to make that extra step from empirical to molecular formulas. Those molecular formulas are also always a multiple of the empirical formula. It is possible to multiply by 1, right? Remember we had our example of here's an empirical formula and here's its molecular formula. Lower numbers do tend to be more common. You're not going to multiply by like 30 or 50 or 206, but it's possible. And the idea here is that that factor between the formulas is always the same as the factor between the masses. So if you divide your molecular mass by your empirical mass, it would be the same number you get if you divided your molecular formula by your empirical formula. You may have to do some additional calculations to get to that molar mass or that molecular mass, but once you have it, you can use it. Thanks for watching.